Let us consider an electric field due to a charged infinite plane sheet. So for this we will take a charged plane sheet. For that we'll take say a plastic or a glass sheet. So let this be a plane sheet. Okay, it's made of glass, and also plastic also, or any metal. Okay, so this is a plane sheet. Okay, let me write down, this is a plane sheet. Okay, plane is flat. Then we are giving positive charge to it. We can also give negative also, but we'll take, for this example we'll take positive charges. Okay, so we given a lot of positive charges to this. Now the electric field, if we see, let's take a point at point P. We'll take this point. So let this point be here. At this point the electric field will be outwards. Okay, because it's a positive charge now. So electric field will be outwards here, like this way. This will be the direction of the electric field. And then let us see, our aim is to find what is electric field. Okay, at this point. So for that we'll choose a Gaussian surface. Remember, Gaussian surface is an imaginary surface. So let's draw a Gaussian surface here. So for this I will draw like a cylinder. Okay, I'll draw cylindrical Gaussian surface like this. Here also. Okay, now you can see the positive charge is on the right side. It will also give a electric field left side also. So on the left side also we can draw a Gaussian surface. Okay, now let this distance, so this point here also will be, you can mark it as P dash. So on the left side this point is P dash. So the electric field will be outwards. So in this case also the electric field will be outwards here. Okay, let's see normal here, area normal. Area normal for this surface. Okay, for this, at this point P, the area normal, we'll take the area as dA, and the area normal here will be dA vector. This will be the area normal, and on this side also we'll have the area normal like this way. So this will be dA vector. Okay, now we must see the distance here. Okay, if you see this distance between the charged surface and the point P, the distance we say it as R, and this side also same distance only. The distance is R. Now we can see this plane sheet has a surface. Okay, it has a surface charge density. The surface charge density we say it as sigma. Okay, now our aim is to find what is the electric flux here. Okay, let's go to and find it. So now let's find the electric flux. Electric flux phi E is equal to closed integral of E vector dot dA vector. Okay, so E means electric field, dA is the area normal. But now you see there are three portions here. Okay, first one is this one. Okay, this point P. At this point P we have an electric field, and at this point also. But now you see here also on the curved surface. On the curved surface also you can see the area normal will be like this way, dA normal. I'll turn and show it to you. This dA normal will be like this way, and the electric field will be like this way. Now let us see this. What will be the value of the total electric flux? That will be equal to the electric flux due to the curved surface. So this will be the curved surface. This is a Gaussian cylinder. Okay, see this thing. This is a Gaussian cylinder, Gaussian surface, or you can say cylinder in this case. So right surface itself. So first one will be the electric or the electric flux due to the curved surface. So we'll write here curved surface. Okay, spelling mistake. Okay, then plus this one. Remember there's a difference here. This is a closed integral and this is not closed integrals. plus the electric flux due to the point P at the point P. Then the electric flux E vector dot dA vector at the point P dash. Okay, so we have three fluxes, we must add them. Now this we can use the formula A vector dot B vector is AB cos theta. I'm going to use the formula here. Write down here. We know A vector dot B vector is equal to AB cos theta. Let's use that formula and find what's the answer for this. Okay, let's find this now. Write it down. For the curved surface, so that will be EDA cos theta. Now for curved surface, let's see the picture again. So this is a Gaussian surface and this is a curved surface here. Now you can see the angle here between the electric field and this thing, that will be 90 degrees. So theta is equal to 90 degrees for the curved surface. So let me write that down. Cos 90 for this one. Then for second one, that will be EDA and then cos, this for point P now. So what will be the cos of this? You see this in this case, the angle here, the electric field and this area normal both in the same direction. So angle between them is 0 degrees. So this will be cos 0 plus integral of EDA and this is cos. On left side you see the electric field and the area normal both in the same direction for point P dash now. So we can write here this also is cos 0. The angle is 0 degrees. That will be cos 0. This is point P dash. Now what is cos 90? Cos 90 is 0. So the first term fully will become as 0. We can take the second one, cos 0. Cos 0 value is 1. Here's third one, cos 0 value is 1. So if you see, the first one is 0. Okay, leave that. The second one for this will be EDA. Cos 0 is 1 for point P. Then plus second one will be EDA. This for point P dash. Left side what we have the electric flux phi E. Okay, now you see that point P and point P dash are the same distance only. Okay, so we can write them as P itself. Okay, so you can add them together. So we get here phi E is equal to closed or integral of 2EDA for point P. Okay, so this is one thing. So let me write it as equation 1. This is the most simple way. Then we'll use a Gauss law. Okay, so from Gauss law. So Gauss law what does it state? The electric flux is equal to the charge enclosed, Q enclosed by epsilon naught. Okay, this is equation 2. Okay, now left side we have this phi E, here is phi E. So we can equate the right sides. Okay, let's do that and see. So let's equate them. So what we get here for first one, we get here that is, oh, I'll write here equating 1 and 2. I'll write the step. Equating 1 and 2. So because left side is same, right side also must be same. So on the left side for first one we get here integral of P and then we have here EDA. That's the right side will be equal to Q enclosed by epsilon naught. Okay, now if you see, this is 2E. Okay, this is 2EDA. Now 2E is a constant, electric field is a constant, so we can take it out. So what we have is 2E integral of dA, okay, limit from P at point P is equal to Q enclosed by epsilon. We're going step by step. Okay, now what does this dA means? The area of this or area of the charge surface. Okay, so if you see the area of charge surface, it was like a square only. So this one is a small area means dA, but you take the full one. Okay, if you take full one, that full thing, this small thing is dA. If you take full thing, that means you summate all the or sum all the small elements, we get here that is will be EA. Okay, so if you add all the small areas, you get the total area as A. So instead of writing integral of dA, we write as A itself. So let me write that down. So we have here 2EA is equal to Q enclosed. Okay, we'll come to next step now. Q enclosed by epsilon naught. Now we know that this is surface charge density. Okay, surface charge density sigma is equal to Q by A. This we have learned earlier. Now what you must do, you cross multiply this A upwards. So what we have is this way. We have and rearrange Q is equal to sigma into A. Now substitute here, substitute in the equation. Okay, so what we have is 2EA is equal to sigma, instead of this Q enclosed we have sigma into A by epsilon naught. Okay, now A and A will cancel and 2 comes down. So we have E is equal to sigma by 2 epsilon naught. This is the formula that we need for the electric field. Okay, this is the formula that we need. Okay, this means here E means electric field, sigma is the surface density, epsilon naught is the permittivity of free space. Now if you see in vector form, you have the electric field E vector is equal to sigma by 2 epsilon naught into n cap. Okay, n cap will show us the direction. Okay, now some things you must know from this. Say if the sigma is greater than 0, sigma means surface density is greater than 0, then what happens, the electric field will be outwards. Okay, this will be happen for a positive charge. Suppose for negative charge, what will happen, sigma will be less than 0. Sigma means surface density. Then what will happen, then electric field will point inwards. Okay, this is a very important 5-mark question. Okay, now let us see, can we do it in real life? Can we see the electric field due to charged infinite plane sheet in real life? Now I have switched off a TV. Let me bring an electroscope nearby and see that. Okay, now I bring it close by. You can see the leaves will diverge. See that leaves diverge here. See that. Okay, now see it. The leaves have diverged because the TV is like a infinite. It's like a plane sheet. It's not infinite, but it's like a plane sheet, and it gives an electric field. Okay, so this will prove that there's an electric field around a plane sheet.